is my pleasure to introduce Roberto Peon, software engineer from Facebook. We're excited to welcome Facebook, who's been working on improving video-related infrastructure across networking, computation, and storage. Before Facebook, Roberto worked at Google for 12 years, with the last 2 at YouTube. Prior to Google, Roberto implemented real-time augmented reality for sports TV, including for those football fans, that yellow line that moves the goal line, the line of scrimmage, and on NASCAR, for those fans, the pointers that are on the screen there. So with that, thank you for joining us.
Thank you.
Look forward to a great presentation.
All right. Hello, everyone. Let's make sure. Thank you.
And please give a big hand welcoming Roberto.
All right. So hey, I'm Roberto Peon. Good morning, everybody. It's early in the morning for some of us, certainly me. Thank you for being here, and thank you for letting me talk about this. I think it's going to be fun. So let's talk about abstractions. After all, as we know from multiple famous quotes, all problems in computer science can be solved by another layer of indirection, aka abstraction. So let's jump into this by figuring out, like, why am I here? Like, why am I talking to you? I'm supposed to be working on video, right? Well, it turns out that for a large-scale video site, there is a wealth of different devices, and they're uploading a wealth of different formats, and they're at different bit rates, and they have different codecs, and they each have different lengths. And so basically, it turns out that there are many different kinds of video and video playback. And even worse, not only are there different inputs, but there are many outputs. And they can each be consumed quite differently. And so in particular, here is an example of what large video processing site may kind of look like. And you notice the storage is kind of in the center there, and it's probably for a reason. And all I can really say is that processing video at scale really requires a bunch of system components working together. So let's talk about video. It turns out that chatting with my mom on video conference is really different than playing that new Netflix series, or watching that new Facebook Watch thing, or whatever is your favorite video channel. And by the way, chatting with my dad has different requirements than chatting with my mom on VC. Right? And the audio part of that has different requirements than the video part. And not all parts of the video, video being a stateful thing, are the same either. And so much so that even as we transfer this stuff along this internet that has become so useful for us, there are different protocols for this. And just off the top of my head, there's RTMP, WebRTC, variants of Dash, there's HLS, and you can probably make up a whole lot more as you go on. And this brings me to kind of the problem. Like, why did I get here? Like, well, I'm lazy. I hope you are all lazy too in this way, because hopefully it's in a good way. I'm lazy, and that makes me not want to have to solve the same problem again and again and again. I want to solve a problem once, if possible, and then map it to all of the other times I have to do the same thing. So the way this translates for me is I want to reuse code. And I want to reuse it for video conferencing and live broadcasts, 1 to millions. And for VOD video, I've uploaded a cat video. And I want to do it between real time and batch, right? And I'll point out, like, from a statistical sense, if I'm not reusing code, I'm increasing the amount of time necessary to achieve a particular certainty about a result, right? Statistic is statistics regardless of the field you're in. And in other words, there's a lot of value in reuse, right? If I want to move my system, my video system, faster, right, I need to be able to trust the components upon which it's built. I can't just reinvent everything every time. That's going to be really slow. Just in an experimental sense, I'd have to take a long time and a lot of experiments to get certainty about what I'm doing. So sadly, when I got to Facebook, there was no abstraction that would allow the reuse of code. across all of these different video use cases. As a reminder, if you're doing video conferencing, surprisingly, you prefer LIFO over FIFO. You prefer the new data over the old data. You prefer low jitter. You don't want to talk like that, right? We humans have our own built-in protocols for flow control and retransmit, right? We don't need some other layer to attempt to do it for us. It confuses the heck out of us, apparently. And so when ingesting a new movie, however, you really want all those bytes, and it's okay to retransmit those things. That's fine, all right? So how do you solve this? As intimated before, add a layer of abstraction, as usual, right? So let me ask you a question to think about in your mind. What I/O abstraction works for partial reliability, right? Partial reliability, to remind everybody, means I may want it retransmitted, I may not want it retransmitted. I may want it retransmitted within a certain reliability window, right? So what abstraction works for that? And if I had to guess, what many people would think is maybe Datagrams or something like Datagrams, right? And I already see some head shakes, and I think I agree with that. Datagrams are insufficient, right? You need an ID somewhere in that datagram in order to reorder. And once you put an ID into that datagram, guess what? It's not a datagram. It's not a unique atomic unit of anything anymore, right? It is now part of some different address space, okay? And by the way, when you send a packet, what is the probability that it arrives on the other side? It's not 100%, right? Because it's not 100%, that means you have to deal with reordering, putting things back in the right order. And I want to remind people, I'm here because of video. And video is inherently stateful. We have these I frames, P frames, B frames. The I means independent, by the way. And all in order to deliver you these wonderful, entertaining experiences that you probably come to enjoy. I can't do that if I'm sending you raw pixels. It's not going to work. And if I have to get all the bytes out of order, I cannot present to you those pixels in any fashion that you would enjoy. So what is my answer to this? Well, my answer to this is that you want a named stream with an offset. And why is it named? It's named because if it's not named, then it can't work. If we go back to how we make computers work at all, I think it's really interesting to realize that the Turing machine requires addressing. It requires offsets. It requires tape in the model, right? And in order to seek in that tape, there has to be some place to seek to, right? So the only way we get computing is because we have addressing. And for me, that was kind of a surprising thing to realize. And I'm going to point out that if we're thinking about other abstractions for I/O, like a socket or a TCP connection that you might be used to, that itself has a name as well, right? Source port, dest IP, source IP, dest port. And of course, in other words, we call it the 4-tuple or the 5-tuple. So it has a name. And so my observation is that this sounds really similar. It sounds like something that we've all been dealing with for a very long time, which we might call the file interface, right? Files have names, they have offsets, they have data, hopefully. And the interesting thing, though, is that I think that the file interface needs a tweak in order to handle this stuff. So if I wanted to represent a TCP stream as a file, what would that look like? And by the way, my opinion is that TCP is really a windowed log. It's not a byte stream. It's a windowed log because we need a buffer in order to do the reordering for the retransmits. That's the log part, right? It's windowed because we want to be able to have an infinite byte stream, but we have a limited address space, right? So the tweak that I want is that when you do a read at an offset that is not yet unknown, right? We haven't yet received the data for it. That read should block until at least 1 byte within that range exists, or until it can be guaranteed that that data is never going to exist. For instance, because somebody has closed the file and said they're never going to change it again. So the sockets API, right, gives us 2 different modes of operation today. Either completely unordered datagrams or completely ordered delivery of data. And in my opinion, neither of those is really desirable. Most data, as we've talked about multiple times now, encompasses multiple packets, right? I mean, it's pretty rare. Even your telnet session from ages past is going to have characters in different packets, yes, but they have some relationship to each other. So presenting your I/O in scatter-gather, which is to say every byte that you give back has an offset, has a range, but every byte that you get may not be in order. It is ordered, but not necessarily in order, right? And once you do that, then you can have proxies and stuff. And the great thing about having proxies in this case is the proxies can help you deal with terminating of that loss, that inevitable loss that happens on every network that has noise, by the way, which is every network and every circuit, all right? So I'm going to make an assertion now. That file interface that I was talking about allows for both normal in-order delivery, which is to say ye old sockets API, without any real additional complexity, but it also allows for out-of-order delivery. And once that's true, I think I probably have an abstraction that I can work with for video. Because again, I have to deal with live video conferencing where I don't want that to happen, right? One moment. And I have to deal with VOD video where I really do care about everything getting everything reliable, and I don't care about the retransmissions. All right, so why does that out-of-order delivery matter? Well, turns out most cases for video, I don't have multicast. At least not at internet scale. I might get it to work for a network or two, but on the whole, it's not working. But thankfully, we do have the CDN. And that basically implies that our solution to scaling is going to be caching. So in order to cache, I have to have the data. I have to address the data. And in order to receive that data, I have to use some API. And if I'm using the socket API, I only have the choice to use in-order delivery, which means I am guaranteed jitter. I'm guaranteed reordering problems, right? So put it another way. Imagine that I have to read k bytes at offset n from a file, and then I have to discard all the n-1 bytes. That is the socket API, right? Wouldn't it be cheaper just to start reading at byte n, right? Isn't that what we're used to with the file interface? All right, so let's zoom into a proxy and talk packets, just to pound this nail even harder, because apparently I only have one hammer. So here we go. Here we are sending packets. Isn't that lovely? Isn't that boring? And by the way, the proxy here that I'm talking about is a CDN proxy, which means we're talking layer 7 HTTP right now, but it really applies to anything where we are trying to interpret stuff. Okay, so boring. All right, let's add some packet loss. Let's make this real. All right, so we got our request, and oops, we missed a packet. And in this case, we missed the first packet of the response. And that there's a interesting possibility that any packet that's lost is not the last packet, and it's pretty high. And I'll point out that on the real interwebs, this can happen even on a supposedly uncontended link because of the way TCP congestion tries to probe bandwidth. So you can contend with yourself. Isn't that one lovely, right? Okay, so what's happened then is that we had to wait for that packet, the one that was lost, to be retransmitted before we could use any of the bandwidth on the further upstream, right? And that's not going to be very work conserving. In other words, that proxy couldn't forward any of that response until it could fill in that hole, right? And we know this by other terms. We know this is head-of-line blocking. And head-of-line blocking is the cause of jitter and variance and all of those things that I'm trying to avoid. And oh, by the way, this head-of-line blocking is also responsible for missing out on some good put that we could otherwise use. In other words, the transmission delay is going to occur for every single one of those packets that followed that first packet, right? That's a cumulative delay because of one packet loss. So problem, videos almost all represented as files, but Facebook didn't have a file interface. I'm going to point out that in many cases when somebody says problem, they're also talking opportunity. Another problem, Facebook had many file interfaces. Huzzah. The great thing about standards is you can always add another one. So that's what we did. We said, hey, let's add another file interface. And that ended up being this thing called OIL+VCache that I'm speaking to you about today. And hopefully, like every other standard we add, this one is different. We're going to get into those differences. But I think one of the interesting things is that we are hoping this is expressive enough to wrap or encapsulate the public interfaces for most file systems and object stores. Right? So what I'm going to try and talk to you about is the fact that I believe that we should be thinking about how to abstract these things in a way that is consistent. In other words, I think that we need to think about innovating the abstraction, and we haven't for a very long time. So back to your regularly scheduled programming, file APIs. Who here likes file APIs? Awesome. Yes, let's talk about file APIs. You're probably used to something like this, right? Open, read, close, write, delete, blah, blah, blah. And my question to you is, what else do you need? Don't have to answer, just think about it. And let's answer that question with a question. What is stored into retval and what is an error no, given this little code snippet? All right, so I'm doing a write of some data. I've already asserted that the file descriptor is valid. Like, what is that return value? All right? And my response is that the question's ill-formed. It depends on the file system. It depends on the quota, the capacity, the load, the contention on the network, the power situation, the heat situation. I mean, it's a trick question. So let's go to another little situation to try and explain this. So what if write is speaking to a distributed system, because nobody here has any of those. And you want to have 3 replicas for safety reasons. And 2 hosts fail the write and 1 succeeds. Here we go. Right, here we are starting off, we have our client who's doing the write and is going to try and talk to these 3 things, and oops, 2 of them fail. Okay, so what's the return value for this system? Right? For banking, that's going to be a hard no, thank you very much. I like my balance to actually make sense, and so does the bank. So the bank, they really care about quorum. They really want consistency in their system. And if they can't have consistency, they're going to give up on availability. Thank you, CAP theorem. But for video conferencing, hey, 1 out of 3 ain't bad, guys. You know? In the video conferencing case, we're good to go, right? So here we have 2 examples where we have the same write call, we have the same nodes, and yet the response is different. Wait, what the? How do we encode that in somewhere, right? So the answer to something apparently as simple as does write return an error depends on the trade-offs of the file system, which tends to be correlated with the trade-offs of the application that people are trying to solve. And we know, by the way, that the P in CAP, the partitioning part of CAP, that's really not optional. Any real system is going to have to deal with partitioning. That's going to happen. Right? So you only get the choice between C and A, or CA and price in most cases. So there's no single correct answer to that question, as we already saw. So why should you care? And I would say, in the case of a single host, those failure domains overlap, and you probably don't have to care. You can pretend you don't need to care. It's good enough. But to typical distributed systems, at least today, those failure domains are so separated and distinct, you probably do need to care if you're going to have a system that people actually want to use. So although, in theory, your computer is internally a distributed systems and the buses are networks and all that kind of stuff, in practice, they're a bit different. And that's probably why our file APIs look the way they look. So other than what I talked about before about just having read block when data is missing, although I do think that is cool. And I think that we should have an API that works for the single host case and at a large distributed system. And I believe that the cost for this abstraction should be low enough on the developers that they actually want to use it. Because otherwise we can come up with all kinds of fairy tales and rainbow dust, and it's not going to happen. And the basic idea of this proposed new API is be explicit. Say what you want. Say what you expect. And hopefully it doesn't have to be that hard. And I'm going to show you a snippet of code here that gives an example, and you will note it is more complicated than the prior code, but hopefully this would be at a lower layer than what you would use, because hopefully the application ends up defining its own right. But the basic observation is we're going to give a policy DAG at the point where we are creating a file. And this policy DAG is going to tell us what should happen in that case where there was 2 out of 3 that failed and 1 succeeded, right? So, first point, create requires a DAG. And that DAG is a specification, which I'll get to later about what that is. The DAG defines a virtual file system, kind of on a per file basis. So I could have what appears to be a completely different file system for any file I create. Practically, people are going to have some set number that they use at any one point in time. They're probably going to change those over time. And I'm not just talking about because my video is 10 years old and the chance that somebody's going to watch it is about the same as lightning striking me here on the stage right now. But also because people have applications that change in their latency requirements, their storage requirements, and all that kind of stuff over time. Operations should have multiple returns because there are at least 2 phases that are interesting in any I/O. And one is that the I/O has been satisfied, and the other is that the effort is exhausted. And satisfied means that the application has said, hey, I can make forward progress now, right? And exhausted means that there's no more work happening in the background, and I can probably deallocate all of my buffers or any such thing that I have. And by the way, the lack of one of these is always going to cause a problem, either in latency and jitter, or in ooming. And we all love ooming because that makes forward progress so easy. So let me ask a question that I had to ask myself, like, what is a file system? And for me, the definition is that it's a mapping of name to byte stream. And really, it's 2 mappings. So there's name to something, and then offset to byte, right? And then the something is really metadata, right? Like this file was created by blah, it's in this place, this is its name, maybe this is the encryption key, because we love encryption at rest these days. And so if we're going to be explicit about everything, then not only do we need to handle like the data part of this, but we need to handle the metadata. So this DAG, to be true in this case, says that for metadata, I'm going to write this metadata to database A. And by the way, these nodes represent systems, not necessarily a specific instantiation, not necessarily a specific host. Okay, but they could be that, depending on what the DAG author is trying to do. So, and by the way, these could all be on the same machine as well. So I'm going to talk to database A for my metadata, and for my data, I'm going to talk to 3 different file systems here, A, B, and C. So let's go back to this. What is a DAG? I hope we all know, but it's nodes and edges. And it's nodes and edges that don't go in a circle. In the context of this new thing, like what is a node? A node is either the built-in race node, which I will get back to, which says how to use its children and when, or it's a storage node, which represents a potential storage location. Each of these nodes could have a transform stack to say how to transform the address space and the data that we want to store in that apparent location. And I'm going to point out that this is a potentially strong win for efficiency. Because let's say I want to encrypt something on disk or at rest, right? Do I need to encrypt it every time I send it to the storage medium and then decrypt it every time I read it from the storage medium, even when some of those storage mediums are buffers somewhere, right? That would be kind of sad. How about I encrypt it once and then know it's supposed to be encrypted in a bunch of locations and then like just shove those bits across the wire and write them? Right? It would be a waste to have to unencrypt them and re-encrypt them every time unless you have a specific purpose in doing so. Some other example transforms, chunking. Hey, if you have a, I don't know, 25 terabyte file, do you really want to try and write that in one storage device? Well, that would be a little problematic, right? Because we don't have all that many storage devices that large. And if we were worried about things like, caching, where you probably have RAM, whether it be DRAM or NVRAM or some other variant, you probably want to be able to actually fit that into your device. So you probably want to chunk it. And we know that loss happens, so how about some read Solomon or other FEC? And we know that entropy happens, so how about gzipped? And of course, we talked about encrypting. So chunking is by far the most common transform that anybody wants everywhere, Every single phone in everybody's pockets does this in the form of virtual memory. It breaks stuff up into pages. These pages are written ostensibly a little separately, although the file system glues them together, right? And the idea here is that since every node in that DAG that I presented before is explicitly labeled with the transforms that we want to do to the address space and the data, anytime you want to write from one to the other, you just simply compare those stacks of transforms, and the stacks are the same. You know, you don't have to do anything more. All right? So here's some examples. In the top example, I'm chunking at 1 megabyte and I'm encrypting. And I'm sending to another node that's doing the same. Don't have to do anything. In the next node, the chunk size is different between these two things. So I have to rechunk, which is incredibly cheap. And in the last one, everything is different. So I have to unencrypt it and I have to rechunk it. All right? OK, so that race thing, this is the clue. This is what makes the magic happen. And it's my favorite part of this new OIL thing. So race is a built-in node. It's not a storage node. It's what we would call a virtual node or some other thing like that. And it expresses that when a certain number has been exceeded, the operation is satisfied and can make forward progress. So you see num until satisfied is 2 in this case, which means 2 children would have to return that they are satisfied. And then this node would return it is satisfied. OK? And then the next line here says num until exhausted. And as a reminder, exhausted means I'm not going to do anything anymore. It means I'm done. But we wanted to avoid saying done because done typically implies success, and exhausted doesn't necessarily imply success. So num until exhausted, in this case 3. Staggered start delay, you know, because we all know that when we have 3 replicas that all supposed to have the same data, we should always read from all 3 of them in order to supply the user's response, right? That would be wonderfully work conserving and cheap. Right? So a staggered start allows us to talk about time, not just about what the semantics of completion are. And lastly, concurrency. We might not want to try every branch at every time, regardless of time. Right? So we want to talk about max concurrency. And it turns out that this little node here is expressive enough to allow you to define an if-then-else chain. Any if-then-else chain, really. If that, OK, great. So basically, in this case, what happened is we did file system A, and that didn't work. So then we did file system B, and that didn't work, so we did file system C. Right? And as max concurrency of 1 implies a serial behavior, right? This implies that in this particular DAG, the nodes have to be visited from left to right. It's also expressive enough to describe try all, because there are actually cases, like when you're doing quorum reads for something, where you do want to try all of them simultaneously. And in this case, we changed max concurrency to 3. And as you'd expect, that's fully parallel. And it's expressive enough to describe a quorum right. Right? So in this case, what we did is we now have number of satisfied 2 out of 3. Right? And as long as 2 of those come back, you're OK. So do you remember that question I asked before? We had 3 different places we were going to write to. And we said, hey, what is the return value for this? Right? Well, I'll point out that num satisfied 2 answers that question. That the return value, if 2 of them succeed, is good. Forward progress can be made. That means that we have told the write call what its response should be in this policy. Not just how to do the write, but how to interpret the success or failure of that write. All right? So let's go back and talk about storage nodes in this DAG. Like, what could those be? They could be things like a local file system, haystack, HDFS, a block device, somebody else's block device, a remote block device. Anyway, they could be anything where you want to store something. And by the way, they could also be something where you don't want to store something, which is useful for testing. So maybe I want a null device somewhere or a tracing device somewhere. Right? Because these are policies, I can insert such things and help me debug my system. I can put fault injectors into my system to say, hey, well, what happens if my metadata server over here goes away and such like that, right? And I can do so without disrupting things, or hopefully without disrupting things. So what does it take to add a storage node into this thing? Of course, you have to write a wrapper. And you often have to write 2 wrappers, one for the metadata and one for the data. And it's mostly boilerplate, as I think one would sadly hope. So data nodes must express things like pwrite, pread, probably stat, a few other things. And metadata nodes must express a put and a get, because the metadata is not streaming, it is atomic, unlike the data, which can be streaming. So what about the edges in the DAG? Like I talked about the nodes, and I said you can wire these things up, but like, what about the edges? So the idea is that the edges could also maybe express the protocol or the QoS that you want to use, because again, not every portion of somebody's read is equivalent. One other thing that's really interesting here is that when this DAG is executed, we are building up a stack as we are progressing down into this tree. And so we're passing a dictionary of read-only values into each node as we proceed downward. And let's talk about another thing that is super important for anything I/O, because all of our I/O is effectively this. What about buffering? So you notice I've talked about OIL, but I haven't talked about this VCache thing, right? So it turns out that it's not an afterthought, that one of the reasons why we had to build this in the first place is because we had to think about buffering. That buffering was intensely critical, not only to deliver on the user's latency expectations in many cases, but also because you actually want to process the data in ways that don't strand your compute units just sitting there waiting for stuff for a long time, right? So in addition to that DAG, we also have a VCache storage node. So I'm putting those together, we get OIL and VCache. OIL is the output-input language. Aren't you happy I defined that now? And VCache is the virtual cache, or the virtual memory cache. The V, surprisingly, does not stand for video. Because I'll note that on every big machine that we actually do computing on, we have virtual memory to try and abstract away the storage from the application. But apparently, in distributed systems, we forgot about that. So here we are relearning, or at least I was relearning. So VCache knows about dirty pages, clean pages, and files. It's accessed using OIL DAGs, and it knows how to talk OIL out the back end for evictions. So it's different from other caches because it understands OIL on both sides. It also does stuff like understanding dirty pages. In other words, it is a write-back cache, which is different from some. And because it's written to and evicts using OIL DAGs, the DAG that we hand over represents a holistic policy. This policy doesn't terminate at any one node in this DAG. Everybody in this DAG can understand where they are participating in that DAG, right? And why would you care? And I'll say again, in my opinion, real-world performance is going to be dependent on how you cache and how you buffer, right? That is where we get most of our performance, given the non-uniform access times to many different places in storage. So VCache understands various write modes, as you would expect. Write back immediate, so your operation is asynchronous. And write back lazy, and all those other kinds of things. And the programmers do use them sometimes. Most of the time, write back lazy is what most people want, because there is a reliability trade-off you get by giving up what I'll call knowability. What about the read path? Well, it turns out reads often have side effects too, although we often forget them. In the cache, a read can cause a cache insert, or it can cause the item to be promoted to the top of the LRU, right? And these have significant impacts, and I'm not going to go into it too much because we have limited time. So what about virtual memory? The interesting thing I came to realize is that the kernels in the various operating systems are all providing a super interesting abstraction. This key byte stream thing that I'm using actually is represented in multiple places simultaneously within the system, right? It's in the L1, the L2, the L3, it's in DRAM, it's in the drive's buffer cache, and it's probably on the drive's storage itself. A piece of data exists in all of these locations, not one of these locations. And in the typical I/O system, we imagine that the data is stored in one place, not that it can be resident in any of these places, right? At least that was new for me. And so that is true of VCache. You can have a VCache that's localhost only, right? So it has the same failure domain of the host in case we want to have those kinds of system properties. But you can also have ones that are remote. You can have ones that are remote within the same rack, data center, et cetera, right? So a vCache then is going to be accessed by saying, I'm going to talk to this vCache, and I want to talk about this file name or this object. So a real-world example here, I'm going to have a local vCache which is going to race to a quorum of remote vCaches, and then they are going to write out to some other file system asynchronously. Right? This is going to allow me to absorb a high number of IOPS, provide a reasonable performance, and still store stuff permanently. Right? Okay. And let's see. So it's a cache hierarchy, right? We have multiple caches. We go through one to get to the other. We can do different hierarchies on read versus write, right? All right. So why bother? I'll point out that you don't often know when you're running a large system if the processes that are communicating are on the same box or not. Right? And if they are on the same box, it's way faster to just share the DRAM than it is to serialize over the network, put it through a socket, put it through the stack, unserialize it, read it. Right? That's way more work for our boxes. So we can do better by understanding where the reads and the writes are homed in that specific circumstance. Another thing about metadata, so consistency is pretty darn desirable. And so these DAGs are expressive enough to express Paxos, it turns out. So you can actually just have a policy as opposed to a system design that allows you to assert whatever consistency you want. And you can do this on the metadata as well as the data, because remember, CAP theorem says you get to choose C or A. P is not optional, except for price. Okay, so the metadata, as a reminder, is the file name, the leaseholder address, all that kind of stuff. And the address of any particular piece of data is computed using the offset plus the file name and the data DAG. So here's an example of Paxos. This is a DAG that could actually work. I'm not going to go through it too much, but you see that describing Paxos in this little policy language is actually pretty simple. And as an aside, in my opinion, everything is a cache. That file system that you are working so hard, that storage you are working so hard to build, it's a cache. And it might be controversial, but what is a file system? It's a cache with the policy of reject new. Right? So when I'm full, I'm going to reject the new stuff. Right? And here's how I can prove it. I have 3 hosts. They all have 1 terabyte of space, and the user wants to write a terabyte of logical space, and I'm replicating the write to every host. How much space is there? How much data is lost, right? None. But now the client is going to buffer. Wait, what? What happens when the clients go away? Right? Okay. So as before, there's a trick question here. Like, which of those scenarios happens depends on the eviction policy that you want to use. So what would happen if the nth replica was evicted for the n-1th replica in this proposed system? Right? So I'm reducing replication. Now, why do I have replication in the first place? I have replication because I want reliability, right? But in the case where I was requiring that replication, I had a 100% chance of losing 2/3 of my offered data, right? I had a loss of 66% of my data, right? However, if I had simply reduced the replication amount and each host had a 99% probability of being up, right, I could store all of that data and lose at most 1% of it. So thinking about everything as a cache implies thinking about how these systems fail in overload, right? That's all a cache is talking about. It's talking about a policy to associate with a resource, right? And making an assumption about what is appropriate for a user is likely to be wrong in many cases. So in this case, we try not to, right? We try to have the user be explicit about that. So as a reminder, problem. An abstraction with multiple return values doesn't look like POSIX, so how would you use it? And the answer is, hey, new applications can use it, I guess, and maybe the old ones use a fuse mount, where they can at least express that policy or the policy name. So what they are using looks exactly like a file, but they can actually still define those different dependencies, and they can define those different trade-offs that they want to have. So they can use the regular POSIX interface, have an answer to that, what should my return value be, not get quite all of the wonderfulness, but 90% of the wonderfulness. And if you have a hierarchy involving multiple layers of a system, how many I/O attempts will occur? So yeah, I have k layers, and each retries n times, right? K to the n. I don't think that's what they mean by try to grow your business exponentially. Right? Effort should decrease as the system health overall decreases, right? So each I/O can use a subdag. Each I/O can be told, hey, this is how much effort I am doing, because this DAG expresses holistically how you're putting these things together. You can talk about how much effort holistically you want to use. So I can have 3 layers. Each could be allowed 3 retries, but as a sum total, I'm only allowing 3 tries. Right? So I can prevent exponential retries while still allowing retries to occur at each layer of the system. We allow per I/O customization. So if I'm doing a file system scrub, for instance, I do want to access every single location. I want to read every byte that I can read to see what is missing so I can fix it, right? So just because the user has defined a policy once doesn't mean that they want to access it in that way forever, right? And it doesn't mean they want to change it either for the application. It may mean that the system wants to use it differently than the application does. For instance, you want to target specific parts of a DAG. I want to read from that node to see if it still has the data in order to fix it. So there's more, but I don't have time to cover all of this in depth. We could probably spend forever talking about this, and that would be a bad policy. So migration, moving data from one DAG to another, because again, policies change over time. We have a coroutine-based implementation. I can say lots of good things. We have some real-world data. What I can say is it looks good at this point. We have looked into maybe peer-to-peer caching of hot data. So if you have thousands of hosts all attempting to read the same thing, we can scale the number of places that actually can serve it. And we can do this without doing peer-to-peer all the time. You do read, scatter, gather, write. By the way, mmap and remote swap with this kind of policy stuff could be very powerful. And event filtering, because not every application and every level of this DAG wants to receive events from everything beneath it over the ocean, right? So bringing it home, I think OIL+VCache is cool and interesting, but that isn't the real point. I'm hoping that this makes you think and rethink ye old storage abstraction. Should it be what it is right now, or should we innovate there and change it and fix some of the problems that occur when you make a choice, any one choice about many things? That's all I got in the presentation. Thank you very much, and questions? Any questions?
Source code?
Source code. Maybe eventually. The team is definitely interested in open sourcing what we have here. But end of the year is approaching, and various other pressures make it very difficult to spend time open sourcing stuff right now. So the idea is that we will open source what we have eventually, but even if we do, I think that what we have in our implementation is less interesting than you thinking about how you would want to do this. Because the core of this, that race node, I think anyone here can implement that. Or they can hire someone to implement that if they want to. The real core here is just rethinking what the storage API should be, because it's been causing problems. At least I think. Any other questions?
What does it mean for the actual media, like SSDs or hard drives?
What does this mean for the actual media, hard drives and SSDs? Does it mean that those can be more unreliable, or?
I think it means that it would be easier for a user to meld together unreliable things and still have a system that appears to be reliable. That's not the same as saying I would do that. But the observation is that these things are inherently unreliable even when you think they are reliable, because the media itself can be reliable, but the system upon which it's built cannot be. So if you want true reliability, not only do you have diversity in terms of locations and replication, but you have diversity in terms of systems, right? And that's why, as my understanding is, the space shuttle and various other things where lives are on the line, they have system diversity in how the things are coded and presented, and not just the locations.
One last question.
Last question?
Thanks for the presentation, very stimulating. I have a question specifically about how you represent nodes in the DAG. It seems to be very specific to how things are replicated, etc. Would you rather that the user specify how durable or consistent or available the data should be?
So one of the APIs that we have been working on is kind of the DAG chooser or the DAG creator. And of course, there's an infinite number of variations, or effectively so large as to be considered infinite. And so what we are imagining right now is that we create some number of things that we think we like, and we map them onto various use cases we think are interesting. We are also been talking about having introspection on the node, so the node can say, hey, I'm a write only, or I'm a append only, or a write once kind of thing, so that you can basically prove properties on the DAG, like everything's encrypted at rest for a bunch of stuff that matters. In other words, the idea is that the user could present a bunch of properties that they want, and then we can select amongst the DAGs that have been described, and if those don't work, maybe try to synthesize another one. In other words, selection of the DAG is wholly separate from the implementation and use of that DAG in the real systems. Thank you so much, everybody.